Hi, so we are switching over to the Open Up resources. We are using Unit 7, Lessons 2, and this is just example number 3. So we're not going over all of the Open Up Unit 7, Lesson 2 examples, just this one that kind of gets to the heart of what exactly we're doing. So this whole lesson is about practicing those exponent rules, and here we're multiplying powers of 10. We're going to eventually use this rule that we talk about today to use other bases that aren't just 10. You can use them with any number or variable, but just for today, we're going to be multiplying powers of 10. So I think what they want us to do first, complete the table to explore patterns in the exponents when multiplying powers of 10. It says we might skip a single box, and we'll just explain at the end why we're skipping it. It'll be pretty easy to see which box that we'll skip here in just a second. So they did the first row for us. So if we have 10 to the second power and we multiply that by 10 to the third power, is there a way that we can write it as just a single power of 10? And the answer is yes. So let's look, the expanded way of writing with exponents helps us visualize. Then we'll figure out our rule, and then we can just use that rule. We don't have to get to an expanded form, which when we get to numbers like this, they get really annoying. So let's take a look. 10 to the second power, we know just based on what an exponent is, that means we multiply 10 by itself twice. That's what 10 times 10 is in that first parentheses. Multiply that by 10 times 3, which is 10 times 10 times 10. How are we able to then move to 10 to the fifth power? Well, we know that multiplication, that operation's closed under the associative and the commutative property. So even if we switched all these numbers around, they're still all 10s. Even if we change the grouping a little bit, so if we were to group all of them together instead of having these two sets of parentheses, you're still multiplying 10 by itself 5 times. So 10 to the second power times 10 to the third power. We can show it all here and show that that's actually just multiplying 10 to the fifth power. You're multiplying 10 5 times, okay? So let's try this again in row 2. So we've got 10 to the fourth power times 10 to the third power. Let's do the expanded version just for good measure right now, so we can visualize. So we've got 10 to the fourth power times 10 to the third power. So it's already kind of getting annoying having to write all of this out. Let's just try to figure out what is our single power of 10 going to be. 10 to the what power? How many times am I multiplying 10 together? 1, 2, 3, 4, 5, 6, 7. So as we look at this, let's try to, in our next example, go a little faster and figure out how can I get this number 7 without having to write it in an expanded form. Where do I get 7 from 3 and 4? Is that the same way you got 5, this first exponent, from 2 and 3? So let's take a look at row 3. Now if I have 10 to the fourth times 10 to the fourth, before we do the expanded version, what do you think it's gonna be? Let's see if you're right. 2, 3, 4, so there's 10 to the fourth the first time, times 10 to the fourth power again. So overall, how many times are you multiplying 10? 1, 2, 3, 4, 5, 6, 7, 8. Is that what you thought? Notice what the rule is. What are we doing? How do you get 8 from 4 and 4? You add them. How do you get 7 from 3 and 4? You add them. 5 from 2 and 3, because we added the exponents. Notice that these all have the same base. Everything is base 10. So as long as, if you notice that you're multiplying two numbers and they have the same base, why do we need to write it any more expanded than just 10 to the fifth, right? There's no reason to split it up like this. So in row 4, let's try to work backwards. They expanded for us. So in this first section, we have 10 times itself 3 times. So we've got 10 to the third, that 1, 2, 3, 4, 5. Times 10 to the fifth. Let's not even look at the expanded version right now. 10 to the third times 10 to the fifth. Because we've realized now we can add all of the exponents together, we should know that our single power of 10 should be 10 to the 5 plus 3 power. 5 plus 3 is 8. Going from here, let's use the expanded version to check. Did you multiply 10 8 times? 1, 2, 3, 4, 5, 6, 7, 8. Yes. So they gave me in my instructions, I'm allowed to skip a single box. I am not about to write all of this out. That's way too much work. But now that we know the rule, right? 10 to the 18th power times 10 to the 23rd power, why don't I just do, what's 18 plus 23? I've got 38, 41. I think that's right. Yeah. So you got 10 to the 41st power. So using that rule, let's answer this first question. Use the pattern I found in the table to write, what if, let's generalize this into, if the same base, right? So all base 10, and we're gonna see later in later unit or later lessons that it doesn't just have to be base 10, it can be any like base. If you're multiplying same base with different exponents, let's just add them together. So how to rewrite this as an equivalent expression with a single exponent. So if we have 10 to the n power times 10 to the m power, that is always going to be equivalent to 10 to the m plus m. Just add them together, okay? So here, what if we have to the 0 power? That doesn't change your rule at all. So if we wrote 10 to the 4th power times 10 to the 0 power, that should be 10 to the 4 plus 0. What's 4 plus 0? Shouldn't matter. So really, if we multiplied something by something else and we got the same thing, aren't we looking at an identity here? Because what's the only number that you can multiply something by and it equals what you started with, right? 10 to the 4th power times what gives me 10 to the 4th power? The only option here is that 10 to the 0 power has to equal 1. The only thing you can multiply by a value and still get that same value is 1. That's the multiplication identity. Okay, that looks like 100, so I'm going to make that easier to read. 10 to the 0 power has to equal 1. And you're going to notice later in later lessons, anything raised to the 0 power is going to be equal to 1. So for now, we can focus on if we see that 0 power, that makes that expression equal to 1. So in our very last example, we've got state of Georgia. Now let's do it in a context. The state of Georgia has roughly 10 to the 7th power of human residents. Each human has roughly 10 to the 13th power of bacteria cells in his or her digestive tract. How many bacteria cells are there in the digestive tracts of all the humans in Georgia? Well, if we know how many people there are, or how many humans, 10 to the 7th power, and you know how many bacteria they all have, which is 10 to the 13th power, let's add them. What's 10 to the 7 plus 13th power? We've got 10 to the 20th power. So that's how many bacteria in all of Georgia. This doesn't seem compelling right now, but what if we were to actually write that number out in expanded form, meaning, and 10 is kind of a nice base because if it's 10 raised to a power, this is how many zeros are going to be after it. That's my little rule of thumb. So another way you can say this, so it's a 1 with 20 zeros after it. 18, 19, 20. What is that? Thousands, millions, billions, trillions. I don't know what's next. There you go. That is a lot of bacteria just of people in the state of Georgia, right? So sometimes it's helpful if you want to have like a huge compelling answer to try to convince somebody of something. It's nice to write it all out in zeros. Otherwise, that was just too long to write in any like practical sense. So a lot of times we use exponents, especially with powers of 10, to describe numbers that are very, very large or very, very small, which you'll see later in scientific notation. So this is kind of our introduction to exponents. Remember, if you multiply with like bases, we can just add the exponents together and write it as a single expression. Okay, so thank you for watching.